Welcome to The Explainer. Today, we're doing something a little different and, honestly, pretty mind-bending. We are taking a simulated, deeply immersive journey straight into the absolute unknown. We're going to explore one of the most mysterious, math-breaking phenomena in the entire universe, flying right into a dark cosmic abyss. Just picture this. You're strapping into a state-of-the-art imaginary spaceship. We've got unlimited fuel, perfect shielding, and we are flying toward an object so incredibly dense, so extreme, that reality as you know it fundamentally changes. Time literally begins to warp, and space itself bends. The big question we're answering today is what actually happens when you cross that ultimate cosmic point of no return? What does it feel like? What do you see? And what does our very best cutting-edge science say is actually waiting for us in the dark? All right, let's start with Section 1, Meet the Black Hole. Before we fly directly into one, we kind of need to define our destination. A black hole isn't actually an empty hole at all. It's really a massive concentration of matter crammed into a shockingly tiny space. The physicist Brian Cox gives a brilliant example for this. Imagine taking our entire sun and squashing it down, just collapsing it continuously until its radius is a mere 3 kilometers. 3 kilometers! If you packed all that mass into a space that small, the gravity at its surface would be so immense that the escape velocity, the speed you need to go just to break free, would actually exceed the speed of light. And since absolutely nothing can travel faster than light, nothing, not even light itself, can escape once it crosses that boundary. And that boundary, as you probably know, is called the event horizon. And the crazy part? They are literally everywhere. Some estimates suggest there are up to 40 quintillion of them in our universe alone. The sheer variety is just staggering. The closest one to Earth, Gaia BH1, is about 1,500 light-years away, while the furthest is a mind-boggling 13 billion light-years away. They range from tiny, stellar mass black holes, like one that's only 3.8 times the mass of our sun, and roughly the size of Manhattan, all the way up to absolute monsters, like TON 618, which weighs 66 billion times our sun's mass. To put that into perspective, you could fit 40 of our entire solar systems across that one single black hole. But real quick, let's squash a massive sci-fi myth right now. Black holes are not cosmic vacuum cleaners. They don't just indiscriminately suck up the universe like a giant space Roomba. From a safe distance, a black hole's gravitational pull is exactly the same as any other object of the exact same mass. Seriously, if you replaced our sun right now with a black hole of the exact same mass, Earth wouldn't get sucked in. It would just get very dark, very cold, and we definitely need some really good winter coats. But the planets would stay in their exact same orbits. Your cosmic vacuum cleaner is totally safe in the closet. Moving on to Section 2, Journey to the Edge. Okay, so we're taking our imaginary spaceship and plotting a course for Sagittarius A star, the supermassive black hole sitting right at the center of our very own Milky Way galaxy. It's about 4.3 million times the mass of our sun, yet it would easily fit inside the orbit of Mercury. As we get closer, we start to see something absolutely incredible. Since a black hole traps light, you obviously can't see the hole itself, but you can see what's falling into it. That's the accretion disk. It's a violently swirling, glowing ring of incredibly hot gas and dust spiraling right around the void. The material is orbiting so fast and so violently that it heats up through intense friction, emitting brilliant light and X-rays. Actually, this is exactly how astronomers usually find black holes in the first place. They spot these unbelievably bright, glowing disks out in the cosmos. But as we approach it edge-on, things get totally bizarre. This is where we see one of Einstein's most famous predictions in action: gravitational lensing. Because the black hole's gravity is so immense, it actually warps the space-time around it. This curvature literally bends the light rays coming from the back of the accretion disk, wrapping them right over the top and under the bottom of the black hole, directly into your eyes. You're essentially seeing the front, top, bottom, and back of the disk all at the exact same time. It's like a giant cosmic funhouse mirror. And you'll also notice one side of that glowing ring looks way, way brighter than the other. Physicists call this relativistic beaming. As that glowing plasma orbits at near light speed, the material racing toward us has its light artificially boosted and concentrated in our direction, while the material racing away is dimmed. It's not just a simple Doppler effect, it's a profound consequence of relativity that makes the disk look wonderfully terribly lopsided. So let's get into Section 3, Crossing the Event Horizon. All right, this is it. We're cutting our engines and just drifting toward the boundary of no return. We're floating weightlessly as we get closer and closer, and this is where the physics gets completely wild. As we fall, there's a total split in reality depending on who is watching. If someone back on Earth was watching us fall through an impossibly powerful telescope, they would actually see our watches slow down. As we got closer to the event horizon, our time would appear to tick slower and slower and slower. To the outside observer, we would literally freeze on the edge of the horizon, slowly fading out and turning red as the light struggles to climb out of the gravity well, a process called infinite redshift. They'd never actually see us fall in. But for us, sitting in the ship, we wouldn't feel a thing. Time ticks totally normally for us. We just fall right past the event horizon without a single second of hesitation. Now hold on, I gotta pause here for a quick misconception check. You've probably heard on the internet that as you fall into a black hole, you can look back and see the entire future of the universe play out and fast forward. That is actually completely false. While time does get incredibly distorted, once you cross the event horizon, you have a very limited, finite amount of time before you hit the center. There simply isn't enough time for the light from the universe's infinite future to catch up to you. See, once you cross that invisible line, space and time essentially swap roles. Space-time starts flowing inward, faster than the speed of light. Inside a black hole, the center isn't just a place in space, it is quite literally your future. Every single direction points inward, and as physicists running simulations have noted, if you were to panic and fire your jetpack to try and escape, you'd actually hit the center faster. No way, right? But it's true, because any acceleration just eats up your remaining time. You are trapped in a river of space flowing exclusively inward. Which brings us to section 4. The spaghettification effect. So we're falling, no way out. What actually happens next? Well, as we plummet deeper, the gravitational pull increases dramatically. But it doesn't increase evenly. The gravity at your feet, which are closer to the center, becomes exponentially stronger than the gravity at your head. You begin to feel a strange, highly violent sensation. You are stretched vertically and squashed horizontally. Physicists have a very real, surprisingly technical term for this: spaghettification. You are literally stretched out like a noodle. Eventually, the forces become so extreme that your body is ripped apart, then your atoms are separated, and then even the subatomic particles themselves are torn away from each other. Now, when exactly does this gruesome little process kick in? Well, that depends entirely on the size of the black hole. If you fall into a small, stellar mass black hole, the gravity gradient is so sharp that you get spaghettified before you even cross the event horizon. You're ripped apart while still in full view of the outside universe. But for our supermassive black hole, Sagittarius A star, the distance to the center is so unimaginably vast that the tidal forces at the horizon are completely harmless. You wouldn't actually be spaghettified until about 0.1 seconds before you hit the very center. You get to enjoy the terrifying ride in one piece right up until the very end. And finally, section 5, the ultimate mystery. This brings us to our final destination on this cosmic journey and the absolute greatest unresolved puzzle in modern physics. At the very center of the black hole is the singularity. Now, it's tempting to think of this as an infinitely dense, physical point in space where all the matter was crushed together. But as Dr. Brian Cox so beautifully explains, because space-time is so wildly distorted here, the singularity is actually a moment in time. It is the literal end of time in Einstein's theory. As Cox puts it, wanting to escape the singularity is like saying, I want to escape tomorrow. You can't run away from tomorrow, right? Because it's in your future. That is exactly how the singularity behaves. It is your unavoidable tomorrow. For a long time, Einstein's math basically said, well, that's the end of the story. You hit the singularity, game over. But then Stephen Hawking came along and realized that black holes aren't completely black. Through some incredibly complex quantum mechanics happening right at the event horizon, they emit a faint temperature, a glow known as Hawking radiation. This means they are constantly losing energy. Over unfathomable eons of time, long after the very last stars in the universe have died, black holes will slowly shrink, evaporate, and eventually disappear entirely, leaving completely normal space behind. But that brilliant discovery totally broke modern physics. It created what we call the information paradox. You see, the fundamental laws of nature state that physical information, the exact quantum arrangement of the atoms that made up you, your spaceship, and everything else, cannot be destroyed. It can be scrambled, sure, but not erased. But if everything that falls into a black hole ends up at the singularity, and the black hole eventually evaporates into random thermal radiation, where does the information go? Is it destroyed? If it is, the foundational laws of quantum mechanics are completely broken. Recent papers published since 2019 are pushing the boundaries here, suggesting that Stephen Hawking's calculations might have missed a subtle detail. They propose that the information actually is imprinted on the Hawking radiation as it escapes, acting almost like a quantum wormhole from the interior to the exterior. The truth is, we just don't have the full picture yet. And studying these collapsed stars is leading physicists to descriptions of the universe that sound straight out of science fiction. It suggests that there is no true inside of a black hole, and that reality itself might best be described as a network of entangled qubits, kind of like a giant quantum computer. Black holes take us right to the absolute limit of what we understand about space, time, and existence itself. So I'll leave you with this to chew on. If all the information of everything that ever falls into a black hole is somehow stored on its surface or scrambled into quantum radiation, is the reality we experience every single day just a holographic projection of entangled information? It's a question that completely breaks the brain, but it guarantees that for sure, the deeper we look into the dark, the more magical and mysterious our universe becomes. Thanks for exploring with me.